This is Bob Capetta, and this lesson is the AND rule of probability. Our first exercise, a coin is tossed and then a die is rolled. Find the probability that the coin lands heads and the die rolls a 6. Well, if we're going to do this, theoretically we need to describe all of the elements of the sample space. That is, all of the equally likely possibilities. Well, the coin is either heads or tails. So let's assume for a second that it's heads. Well, the die could be 1, 2, 3, 4, 5, or 6. So we have heads 1, heads 2, heads 3, heads 4, heads 5, heads 6. Similarly with tails, if it's tails, we could have tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. So our sample space, all equally likely outcomes, includes those 12 items. Our question asks, what's the probability we get heads and 6? Heads and 6 is right here, one possibility out of how many total? One possibility out of 12. So we're able to do that just listing all of the elements in the sample space, but also recognize that there are two separate experiments here. Flip a coin, roll a die. If I'm going to flip a coin, what's my sample space? It's either heads or tails. I can certainly find the probability of heads. The number of winners divided by the total. Number of winners is 1 divided by the total is 2. So my probability of heads is 1/2. How about rolling the die? My sample space includes all 6 items, 1, 2, 3, 4, 5, 6. So my probability of rolling a 6, 1 winner out of 6 total. Probability of 6 is 1/6. But what did we see when we listed the entire sample space for the exercise? Heads and 6 showed up 1 time out of 12. But do you see the relationship between 1/2, 1/6, and 1/12? I hope it's obvious that 1/12 is simply 1/2 times 1/6, which is the probability of heads times the probability of 6. So is that always the case? Is the probability of heads and 6 the probability of heads times the probability of 6? Yes. Is the probability of A and B always simply the probability of A times the probability of B? And the answer is not quite. That will be true if the events are independent. So we need to define that concept. So here we go, AND rule with independent events. Here's the rule. If A and B are independent events, then the probability of A and B is simply the probability of A times the probability of B. But what does it mean to be independent events? Two events are independent events if the occurrence of either of them has no effect on the probability of the other. So if you know what happens in one event, that doesn't change the likelihood of what happens in the other. So in the case of what we just did, what did we have? We had a situation where we rolled a die and flipped a coin. If the coin comes up heads, that doesn't change the likelihood of getting a 6. If the coin comes up tails, that doesn't change the likelihood of getting a 6. What happens on the first coin flip has no influence on what happens on the dice roll. So if that's the case, the events are independent, which enabled us to say probability of heads and 6 was simply probability of heads times probability of 6. But determining whether or not events are independent is going to be an important thing for you to do when using this AND rule. Here we go. A roulette wheel has 18 red spots, 18 black spots, and 2 green spots. If the wheel is spun twice, what is the probability that the wheel lands on red both times? Are they independent? We're spinning the wheel twice. Does what happened on the first spin affect, influence, suggest what will happen on the second? No. Sample space is still the same. We still have 38 spots each time. Each spot is still equally likely. So what happens on the first roulette spin has no effect on what happens on the second. So indeed, these are independent events. And knowing that, then, we can use our rule, which is going to be probability of red on the first and red on the second will simply be probability of red on the first times probability of red on the second. What's my likelihood of red on the first? 18 out of how many? 18 plus 18 plus 2. 18 out of 38. How about probability of red on the second? 18 out of 38. So we get 18 out of 38 times 18 out of 38. So our likelihood of getting red on the first and red on the second is about 22.44%, 0.2244. So again, we've established our rule, right? Our rule being probability of A and B is probability of A times the probability of B if A and B are independent events. But we can also extend this to 3 events. So here's our case, same roulette wheel. If the wheel is spun 3 times, what is the probability that the wheel lands on red all 3 times? Again, 3 spins are independent. What happens on the first spin doesn't change your likelihood of getting red on the second or third. There is no influence from previous spins on later ones. So we can just recognize probability of red 1 and red 2 and red 3 will just enable us, because they're independent, to multiply the probabilities. Probability of red 1 times probability of red 2 times probability of red 3. What do we get red 1? 18 out of 38. Red 2, 18 out of 38. Red 3, 18 out of 38. We put all those together and our probability will be 0.1063. But what enables us to multiply those probabilities is the fact that those events are independent. Let's keep that in mind. Okay, our next example. We're going to select a card from a deck of 52. It is replaced. So we select a card, put it back in the deck, shuffle it up. We're going to select a card again. We want to know whether or not both cards are diamonds. So are these independent events? Is what happens on the first going to cause an effect with what happens on the second? Well, we're putting the card back in the deck. Card goes back in the deck, so there's still 52 cards in the deck. That is not going to change the likelihood of what happens on the second one. Sample spaces in each case include the same 52 cards. They will be independent events. So I want diamond on the first and diamond on the second is simply going to be probability of diamond on the first times the probability of diamond on the second. Now, how many diamonds do we have? 13 diamonds, 13 hearts, 13 clubs, 13 spades. So there's 13 out of 52 diamonds on the first draw. We put the card back in, there's still 13 out of 52 diamonds on the second. So a quarter times a quarter, that'll be a 16th, or 0.0625. Now those events are still independent. Now how do we change it? What if we select a card, put it aside, select another card, put it aside? What happens on the first draw is going to change the likelihood of what happens on the second. Those events are not independent. So here's our example. A card is selected from a deck of 52. It is not replaced in the deck. The card is selected again. Find the probability that both cards are diamonds. So what do we say here? These events are not independent. What happens on the first selection changes the likelihood of the second. If the first card is a diamond, you have a different probability on the second than if the first card was not a diamond. It influences the likelihood of having a diamond on the second draw. So our old rule, probability of A and B equals probability of A times probability of B, does not hold because these events are not independent. We need a general rule. This author calls them with dependent events, but frankly it works with any. So the probability of A and B is the probability of A times the probability of B given that A has occurred. That's our rule. We want to use a more efficient notation, so this is the notation I prefer. Probability of A and B is the probability of A times the probability B occurs knowing that A has occurred. There's a vertical line in between. So that's our standard notation. So if we go back to our question, probability of a diamond on the first and a diamond on the second is probability diamond on the first times probability diamond on the second, knowing that we had a diamond on the first. Now let's think about this. Diamond on the first. There are 13 diamonds out of 52 total. That's my first draw. I know that one's a diamond, so my second draw, there's only 51 cards left. Of them, how many are diamonds? Well, there used to be 13, but now there's only 12 because I know there was a diamond drawn on the first pull. So probability diamond 1, 13 out of 52. Probability diamond on the second, knowing diamond on the first, 12 diamonds left out of 51 total. So in this situation, selecting cards without replacement, without putting it back in the deck, not independent events, we get our answer of 0.0588. And here we're going to extend this rule as well. So we're going to say 3 cards are selected from a deck without replacement again. Find the probability that all 3 cards are diamonds. So diamond on the first, diamond on the second, diamond on the third, not independent. So we had our rule, probability of A times probability of B given A. That we need to also extend. So again, not independent. What happens earlier affects the likelihood of what happens later. So we need to extend our general AND rule. So the first part, probability of A times probability of B given A, will look similar. But then we get probability of C given both A and B, which looks fairly challenging to understand, but in reality you'll see that it follows fairly directly. So here we go. Probability diamond on the first and diamond on the second and diamond on the third equals probability of diamond on the first times probability diamond on the second knowing we had a diamond on the first times probability diamond on the third knowing both diamond on the first and diamond on the second. What's diamond on the first? 13 out of 52. So I know I had a diamond on the first. There's only 51 cards left. How many of them are still diamonds? Well, only 12. So 12 out of 51 would be left. That's also a diamond. So now there's only 50 cards left. How many of them are diamonds? Well, we've burned up 2 of them in our first 2 slots, so we're down to 11 diamonds out of the 50 cards that are left. So that's diamond on the third, knowing the first 2 were diamonds. So 13 out of 52 times 12 out of 51 times 11 out of 50. So really not so bad to manage. Probability all 3 are diamonds, 0.0129. Okay, next up. 5 cards are selected from a deck. We want to determine the probability that none are diamonds. First one, not a diamond. Second one, not a diamond. Third one, not a diamond. Fourth one, not a diamond. How are we going to do this? 13 diamonds and 39 non-diamonds. So probability none of them are diamonds. First, how many non-diamonds? 39 non-diamonds out of 52. Once that's pulled, there's 51 cards left. How many are still non-diamonds? 38 out of 51. Also a non-diamond, so there's 50 cards left. We've now burned 2 non-diamonds. We're now down to 37 non-diamonds out of 50. Burned 3 non-diamonds, 36 non-diamonds out of 49, and finally 35 non-diamonds out of 48. So that's the probability that none of them are diamonds. We selected 5 cards. 1, 2, 3, 4, 5. We could have tried to list the rule. Frankly, the rule is going to be difficult for us to list. Diamond on the first times diamond on the second given diamond on the first times diamond on the third given diamond on the first and diamond on the second times diamond on the fourth given diamond on the first and diamond on the second and diamond on the third times diamond on the fifth given diamond on the first and diamond on the second and diamond on the third and diamond on the fourth. Yes, difficult to manage, but relatively easy to use. If I multiply all these together, the probability that none of them are diamonds is about 22%, 0.2215. Now, one of the questions we always ask in probability theory is the at least one question. So I selected 5 cards from a deck. Now, if I ever ask for at least one, probability of at least one something is 1 minus the probability of none. Complement of none. If it's not none, it's got to be some. Some means at least one. So if I want the probability of at least one diamond, that's 1 minus the probability of no diamonds, which we just did. Up here we showed probability of no diamonds with 5 cards drawn was 0.2215. So at least one diamond is 1 minus the probability of no diamonds. So again, here's our question. 5 cards are selected from a deck. Determine the probability at least one of them is a diamond. We did that previously. Probability of at least one diamond is 1 minus 0.2215, which gives me approximately 0.7785. Let's take a look at one more question in the at least one world. So remember, these were not independent events. This last case will indeed be independent events. 4 coins are tossed. Find the probability at least one is a head. So think about how we're going to change probability of at least one heads into our situation here. So probability of at least one is 1 minus the probability of none. Probability of at least one head is 1 minus the probability of no heads. No heads means what? No heads means all tails. So I need tails on the first, and tails on the second, and tails on the third, and tails on the fourth. So here we go. And then we ask ourselves the very important question. Are these independent events? If these are independent events, I can simply multiply them. Probability tails on the first times probability tails on the second times probability tails on the third times probability tails on the fourth. If they're not independent events, then I need to use the extended rule. But the fact of the matter is tossing coins are always independent events. What happens in the earlier events does not affect the likelihood of what happens in subsequent events. So the fact that these are independent, I can take probability of tails on the first times probability tails on the second times probability tails on the third times probability tails on the fourth. All of those are a half. Every time I flip a coin, there are two possibilities, heads or tails. Tail shows up one time a half. So 1 minus a half, a half, a half, a half, that's a 16th. So we get 1 minus 0.0625. So if I flip a coin 4 times, probability of at least one heads is 0.9375. So let's remind ourselves of our basic concepts here. What did we look at? We had some rules. Our first notion was what? Independent events. If A and B are independent events, probability of A and B is the probability of A times the probability of B. What does it mean for events to be independent? Two events are independent if the occurrence of either of them has no effect on the probability of the other. It doesn't change the likelihood of the other event happening. Rolling a die and flipping a coin were our best example of that. Then what else did we have? Then we had our notion of our general rule, which is the probability of A and B is the probability of A times the probability of B given that A has occurred. That's what we use when the events are not independent. They call this dependent, but the fact of the matter is this works for all events. But our favorite example for non-independent events was pulling cards from a deck without replacement. If I pull a card from a deck, there's 52 in the first draw, there's 51 in the second, the sample space has changed, the probability has changed. Those events are not independent. And that, my friends, is the AND rule for probability.